Hello, students. So today we will begin with the new chapter, which is termed as chemistry of D and F block elements. So in our previous classes, we have covered the sessions on S and P block elements. And as you know, the periodic table consists of S, P, D, and F block elements. So with today's session, we will start the chapter of D and F block elements, where we will start with the D block elements first, and in the later stages, we will move to the F block elements. So we shall start with the typical example where D block elements can be introduced. The first one is on what ground can you say that vanadium, that is having a Z, that is an atomic number is equal to 22, is a transition element, but cadmium, which is Z equal to 48, is not. So before going to answer this question, we have to see how the 3D or the D block elements or the transition elements are located in the periodic table. So firstly, when we have if it is the periodic table, suppose we are having this periodic table, and on the left hand side we have S block elements, and on the extreme right hand side we have this P block elements, and in the middle portion D and F block elements are actually there. So the group start from this left hand side, where we have group 1 and group 2, which are S block elements, and in the right hand side from group 13 to group 18, these are the P block elements. So as we start from group 13 is the boron, aluminium, gallium group. Next we have the carbon group, then we have the nitrogen or nitrogens, then we have oxygen group, that is commonly termed as the chalcogen group, and the last group is the 18th group is the noble gas group. In the left hand side we have this group 1, which is the alkali metal group, and the group 2, which is the alkaline earth metal group. Now in between these S and P block elements, these D and F block elements are sandwiched. So the D block element have 3 series. First one is the 3D series, next one is the 4D series, and the last one is the 5D series. So from top to bottom, as we see, the principal quantum number, that is the N, increases, so the size of the atoms also increase. Now if we will focus on these 3D elements, so 3D element starts from the left hand side as scandium, then we have titanium, then we have vanadium, after that we have chromium, then we will go to manganese, and now we will come to iron. After iron comes this cobalt, then comes nickel, and the last transition metal here, which is copper. After that we have another group, and this group actually starts with zinc, and this is the 3D series. Supposedly here, if we can come to 4D or 5D, there are metals which actually have some similar properties, all with the earlier lighter congener, that is scandium or titanium or the vanadium or any group you can choose. Now if you see from scandium to copper, these are the transition elements. So these are actually termed as the transition elements. If we can take the all total value of all these groups, they are collectively known as the D block elements. So from scandium to zinc, all the elements are D block elements. But there is a difference, slight difference between the transition element and the D block element. So transition elements have some typical definitions. The most acceptable one is the one that is having some incompletely filled 3D orbital, either in its ground state or in its excited state, are termed as the transition element. That's why the question here is saying which one is the transition element. Vanadium is actually a transition element, but cadmium is not. Now both vanadium and vanadium has the symbol as V and cadmium has the symbol as CD. Vanadium's atomic number or Z is equal to 22 and that of cadmium is 48. So cadmium actually lies just beneath zinc. So here is the 4D element, that is cadmium, just below zinc. And after that we have mercury. So this group, this 3D group is actually quite interesting in terms of properties related to the other D block elements. So we will circle this first. This group has some typical characteristic that is not found in the other D block elements. So this is not a transition group. So Tm is actually denoted by the transition metal. So all these atoms that you are seeing here are actually elements, are actually metal. None of them are non-metal. So these D block elements or the F block elements all are characteristically metal. I have told from scandium to copper, from scandium to zinc, all the elements are D block elements. But from scandium to copper, these are the transition elements also. But zinc group does not fall under this transition metal group. So what is the reason? Because the reason actually lies in the definition of a transition element. So when a transition element is such an element which is having vacant d orbital, that is the incompletely filled d orbital, either in its ground state or in its excited state. Excited state means in its oxidized state, and ground state means when the oxidation state is 0. That is the ground state. So now the Z actually starts from scandium as 21. This to titanium is 22. Vanadium is 23. So such wise 1 plus 1 will be the Z or the atomic number of the elements. So titanium has Z22, vanadium has 23, chromium has 24, manganese has 25, iron 26, cobalt 27, nickel 28, copper is 29, and at zinc we will reach to 30. So zinc has this Z is equal to 30. The similar property will be observed for cadmium also. Since the groups are actually having some similar characteristics, so if a rule is actually holding for one element, it will also hold for the same group heavier element. So the same will be applicable for cadmium and the same will be applicable for mercury. The differences will only be in the Z, that is the atomic number. Because you know, as we go down the group, the principal quantum number increases, that is n increases. So Zn has n is equal to 3, cadmium has n is equal to 4, and mercury has n is equal to 5. And their atomic numbers will also be quite different. Now, I have told how the electrons are actually filled up. So after this calcium, so here we are having this S2 block element. Here before scandium, we have calcium. So calcium has some electronic configuration 4s2. So calcium's electron configuration, as we know, that is the S block elements and the group 2 elements have a typical electronic configuration of ns2. So after 4s, there comes the 3d orbital instead of the 4p orbitals. So if we have a look at the this orbital's energy, we will see the energy of 4s is less, and then we will have this 3d orbital before we reach the 4p orbital. So before reaching this 4p orbital, these 3d orbitals have the lower energies. That's why the electrons will be filled in the 3d orbitals before the 4p orbitals. That's why these 3d elements have come into picture. Since the energy of the 3d orbital is lower than that of the 4p orbitals. Now, calcium has the electronic configuration 4s2, and it also has the atomic number Z is equal to 20. So scandium will be 1 plus, that's why candium is 21. So candium's electronic configuration will be 4s2 3d1. That's why scandium's electronic configuration is 4s2 3d1. Likewise, we are having titanium as 4s2 3d2. That's how the electrons will be filled up. So now when we will reach to zinc, that is Zn, Zn has the electronic configuration as 4s2 3d10. So this is the electronic configuration of zinc. Now when we have reached to zinc, so let's draw the electrons in the orbitals and let's see how zinc atoms electrons are fulfilled. So if we see the electron here in the 4s orbital, we will have 2 electrons. So both the electrons will be paired up here, because we know in one orbital they are only being at max 2 electrons, and since according to the Ohm's rule, both the electrons will get paired up. Now we will come to the 3d orbital. So as we know that the 3d orbitals are 5 in number: dx, y, dyz, dzx, dx square y square, and dz square. Now we have 10 electrons in the 3d orbital of zinc. So if we can fill the valence electrons according to Hull's rule, we will first fill all the orbitals one by one electrons. So 5 electrons will be filled, and again the electrons will be filled in the opposite orientation, such that all the electrons get paired up. So 5 plus 5, 5 upward and 5 downward electrons will count for 3d10 electronic configuration. So this is 4s2, all the electrons are paired up, and this is d10, so all the electrons are paired up. So that's why zinc atom has all the electrons in the paired up form, and also no orbital is vacant. So if no such vacant orbital is there, so there is no incomplete 3d orbital, incompletely filled 3d orbital, because all the 3d orbitals are fully filled. That's why when we have this, so same actually hold for the cadmium. So here in case of zinc, what is 4s 3d? In case of cadmium, that will be 5s and 4d. So one quantum number will be plus than the present one. So that's why in the case of cadmium, you see the electronic configuration will be 5s to 4d10. That is the ground state electronic configuration. But according to the definition of a transition element, we have to look for both the ground state and in the excited state. If in any of the cases we have vacant 3 orbitals or incompletely filled 3d orbitals, then we will check the element and we will say that it is a transition element. Now I will inform you about this group. So this group has the principal oxidation state as +2. So all the elements in this group will show a common oxidation state, that is +2. Without +2, there is no such oxidation state that is actually shown by this zinc group. So if we can consider any atom here, suppose it is cadmium 2, or it will be zinc 2, or you can suppose it for as Zn2, or you can say the mercury 2. So since the energy of the 4s orbital is much higher, so firstly, when we will pull off the electrons will go away from the 4s orbital. So if we can draw the electronic configuration of cadmium 2 or Zn2, it will be Nd10. So no d electrons will be touched. In case of Cd, n is equal to 4. In case of zinc, this n is equal to 3. So in this case, whenever in the oxidation state or in the excited state also, the electronic configuration of either zinc or cadmium remains as Nd10. So that's how in none of the cases, either in excited state or in the ground state, this cadmium does not, or zinc or mercury does not have incompletely filled d orbitals. That's why cadmium or zinc is not a transition element, but they are a d block element. When we will come to vanadium, vanadium will have this number as 23. Now we will have this compound actually present. This quantum when we will have this compound vanadium, and now if we can check for the value, so vanadium is having some incompletely filled d orbitals. So vanadium is having this as 23. Now if we can put this d orbital here below vanadium, and we will check for 5 orbitals, and then we will fill up the electrons as 1, there is 2, and the last one is 3. So 3 orbitals are actually filled here. So the configuration of vanadium will be 4s2 3d3. Now you can see we are having vacant orbitals here in vanadium. This one is vacant and this one is vacant. So 2 orbitals are vacant for vanadium in the ground state. And also in the excited state also, we will see the vanadium will have some electronic states. So in these cases, we will see that vanadium has some vacant or incompletely filled 3d orbitals in its ground state. That's why vanadium is termed as the transition element. But cadmium or zinc will not be a transition element. Both vanadium and cadmium or zinc, everyone will be the d block element, but vanadium is a transition element, and from scandium to copper, all the elements are actually transition element. But this zinc group, zinc, cadmium, mercury, are not transition elements. So I hope with this preliminary introduction, with this vast question, we will have a grip. You guys will have a grip on the concept of the 3D elements or on the transition metals or the transition elements. So now we will move on to the next question. So that will actually clarify some other things here. That is actually a tail of the first question that we will discuss here. The question is, silver atom has completely filled 3d orbitals, that is 4d10 in its ground state. How can you say that it is a transition element? So as I have told you, so except zinc, cadmium and mercury, all the 3d block elements are actually transition elements. So silver, which is having the electronic configuration in its ground state as 4d10. 4d10 is the ground state configuration of silver. Still, silver is termed as the transition element. So why it is so? So before answering this question, I will suggest you to have a brief, have concentrated on the definition of a transition element. So the transition element will be the one which will have this vacant 3d orbital. These 3d orbitals are there. So this will be, any of the orbital will be vacant either in its ground state. Ground state is denoted by the GS term, or in the excited state. Now silver actually lies below in the group of the copper. So we have copper in the 3D series, silver in the 4D series, and Au, that is the gold, in the 5D series. So this group actually shows some oxidation state, and the general oxidation state of this group will be +1. So we have this electronic configuration as oxidation state of +1. Ag, in most of the cases, silver actually shows this +1 oxidation state in all the compounds. You can look for this silver oxide where silver is +1. You can look for the AgCl or AgBr or Agi, that is the silver halides, silver chloride, silver bromides, or silver iodide, or you can go to the silver acetate. So in all the cases, silver atom has the oxidation state as +1. So when we have this +1 oxidation state, we will have this electronic configuration as 4d9, because 1 electron will be lost from the valence shell, that is the 4d10. So from 4d10, that is silver 0, we will come to silver plus, that is 4d9 in the excited state. And if we draw the configuration here, we will have some 5 electrons in 5 3D orbitals first, according to the Hund's rule. Then we will fill the orbital as 6, 7, 8, and 9. So we see in the last orbital we have some vacancy. Here we will have a vacancy. So this vacancy will be responsible for the transition metal character of silver. So that's why silver is termed as the transition element. Despite in its ground state, it has completely filled d orbitals. But in the excited state, there is a vacancy or incompleteness. That is why silver is termed as the transition element or the transition metal. Now we will come to the next question. So first one is the why do chromium, molybdenum, and tungsten, these three elements show high melting point values with respect to other transition elements. Now, how this melting point will be considered, how you will be able to answer such questions on the D block elements. When we were discussing about the S block elements or the P block elements, we haven't discussed about these specific kind of questions. But in case of these D block elements, such questions will frequently come into picture, that are both actually required for the examination purpose also. So how we will correlate the metals with their high or low or mediocre melting points or the boiling points. So here one trick that I will be showing you. First one, how you will remember. So firstly, this melting point actually depends on the enthalpy of atomization value. This is termed as the enthalpy of atomization. So that is actually denoted by this specific term symbol, that is delta A H negative. And its specific unit will be, that is most acceptable one, is kilojoule per mole. That is delta A H inverse, the enthalpy of atomization. Now this enthalpy of atomization, if it goes up, then the melting points or the boiling points of the element will also go up. So both melting point and the boiling point will go up. So this melting point or the boiling point of the elements are directly proportional to the enthalpy of atomization. Now, how we will actually count for the elements, how we will explain why this chromium or molybdenum or tungsten actually shows high melting points. So if we have to answer such questions, we will first have to see how these electrons are distributed in the elements. Now we are given this chromium group. So if we can think of the 3D series, we have scandium, then we have titanium, then we have vanadium, then we have chromium. So firstly, this scandium should be starting with this D1, D electron, because we have this calcium 4s2 first. Up to calcium, that is 4s2, the electronic configuration is locked for the element. Now we'll have some Sc scandium, we have D is equal to 1. For titanium, we have D equal to 2, electrons of D equal to 2. Vanadium, we have D3, and the chromium, we have D4. So if we have a glance here, and on the first case, we will have the idea or the notion that the chromium has some electron configuration, which is 4s2, 3d4. But that is not the case actually. The chromium's electronic configuration is not 4s2, 3d4. Rather, it is 4s1, 3d5. So this is the electronic configuration for chromium, not 4s2, 3d4. So this anomaly actually comes twice in the series. First one is in the chromium group, and the later stage we will come to the copper group. So this chromium and copper group has this electronic configurational anomaly, and that can be beautifully explained by this trick. So here, firstly, I will show you how to account for this observation. We have 4s here and we have 3d here. And in this configuration also, we have 4s here, and in this 3d here. Now, if we draw this configuration, we will have this 4s2 here, and we have 4 electrons that are actually unpaired and free here. This is the configuration 4s2 3d4. And now in this configuration, we have 4s1 3d5. So between this one, I have told you that this configuration is not actually observed, but this one is observed. Why it is so? So here the stability of the half filled or the full filled orbital comes into picture. While I taught you about the S block element, or I have told you about the P block elements also, I have told you about the stability gained by the configuration where the orbitals are either half filled or full filled. So how it can be actually here applied here? Here also the half filled or the full filled orbitals will have the more stability. So here in this configuration, the S orbital is full filled because we have the configuration S2. But the D orbital, that is D4, is neither half filled nor full filled because D orbital has the total electrons as 10. So D5 or D10 will be the stable configuration. So here the stability only comes for the 4s orbitals configuration. But if we can actually excite one of the S electrons to one of the vacant D or electrons, then we will reach to this configuration. Now this configuration has some bit amount of high energy because here we have to first break the pairing energy between these two electrons, excite this single electron to this vacant orbital, and we will reach to this electronic configuration, that is 4s1 3d5. From 4s to 3d4, we will reach to the 4s1 3d5 by giving or producing or giving or actually investing some amount of energy, because then we have to break the pairing energy between these two S electrons, excite this one electron to the high energy D orbital, and then actually we will have this configuration 4s1 3d5. But in turn, this configuration will give some extra stability because you have this 4s1 that is actually half filled. The half filled is as stable as the full filled, and now we have this 3d5 that is also half filled. So both this half filled stability will be actually much more, but much more than this alone half full filled stability. So in this configuration, we have just this full filled electronic configuration stability, but in the later case, we have the half filled and the half filled stability. So here it is full filled is FF, and here it is nil. No stability from this configuration. But here it is half filled, that is HF here, and also half filled from this 3D orbital. So both the HFs will actually outsmart the FF stability. That's why chromium actually prefers this 4s1 3d5 electronic configuration. So its electronic configuration will not be 4s2 3d4, but will be 4s1 3d5. But why we were discussing about all these electronic configurations till now? Because the question is not regarding the electronical configuration, but the question is regarding the high melting point observed for the chromium group. So now I will tell you why I discussed about all these things. This was because the number of unpaired electrons has some connection with the enthalpy of atomization. And the enthalpy of atomization has the direct connection with the melting point or the boiling point. So if we have to answer such question, we have to go to the back references. We have to go back and back and back, and ultimately from the core we have to answer. So when the question was on the high melting point, I told you guys like it is the enthalpy of atomization that has some direct correlation with the melting point or the boiling point. And this enthalpy of atomization has some direct correlation with the number of unpaired electrons. That's why I have told you about, discussed all these things about you, how the electrons are actually distributed in the chromium group. Now, as you know, the chromium group has the electronic configuration as NS1, N-1, D5. So it has the electronic configuration as NS1, that is the half field, and the ND5, that is also half field. So this half field configuration give extra stability to the chromium group. Now we have these five unpaired electrons. And as you know, in the d orbital, 5 can be the maximum unpaired electrons number. Because beyond that, if we go to the condition 3d6, the sixth electron will come here and it will get paired up with one of the electrons. And then we will have this electronic configuration d4. So the number of unpaired electrons will be 4. So from d5 we will come to d4. So d5 is the maximum limit of the unpaired electron for a d element or the d block element. Now, as you can see here, I have for your reference, I have written here high enthalpy of atomization value results from the fact that one unpaired electron per d orbital is particularly favorable for strong interatomic interaction. So here you have been given this value as, or the trick here, the trick is nothing but the number of unpaired electrons, if will be more, the more will be the interatomic interaction. So if the number of electrons, unpaired electrons are more, then there will be more interatomic interaction. So the more will be the interatomic interaction, the more will be the enthalpy of atomization, because then the amount of energy required to atomize the element will be high, because there actually occurs some very strong bond or the interatomic interaction or strength between the atoms. And if the enthalpy of atomization is high, automatically the melting points or the boiling points of the elements will be automatically high. So that's how, by going to the back references, you can answer such questions. So I will repeat this for you guys also. First, we have to answer the question why they are showing the high melting points. This melting point has some correlation with the enthalpy of atomization. Now, enthalpy of atomization is actually directly proportional to the interatomic interaction, and the interatomic interaction has some correlation with the number of unpaired electrons. That's why it is very important for us to know how the electrons are distributed in the transition elements or the electronic configurations of each of the elements. So since this chromium has number of unpaired electrons 5, that is the most, that's why their enthalpy of atomization is also high, so their melting points are high. That's why this chromium group, this chromium, molybdenum and tungsten, 3 of them show high melting points. So I hope with this fast discussion, you will be able to answer such question where the melting points or the boiling points are actually asked in the exam, like which element has high melting point, which element has low melting point, or vice versa. Now we will come to a very interesting part of the chapter, which is by actually knowing which we will have this question answered. So the question is account for the very similar radii of zirconium and hafnium. So zirconium or hafnium, we will actually have reached here. Which one is zirconium and you have the hafnium. So if we firstly we have to locate the elements where they are located in the periodic table. So that's why I will ask each of you to first know about the location of the elements. That cannot be actually be taught, but you have to remember where the elements are actually located. That's why you have to memorize the things, how these elements are located in the periodic table. Otherwise, you will not be able to answer such tricky questions. So here I'll tell you, firstly, we have this scandium in the 3D series. Then we have titanium. Then since I know about the positions, I can write easily how they are actually having consequently, but you have to memorize the positions of the elements. So below scandium, we have this yttrium. And below yttrium, we have this lutetium. Now, if we can come to this titanium group, titanium has in the below have this zirconium. That is actually in the question, which is this zirconium. It has this atomic radii of 160 picometer. And below zirconium, they are having hafnium. Below vanadium, we have this niobium, and below niobium, we are having this tantalum. We will not go beyond because this is will be our way of this will be our genre of the region of the question. Here we have this S and P block elements, S block elements, and right hand side we have this P block elements. Here are the other D elements. Now you can see after this we will come to this question how we can actually answer this. Firstly, we have this barium. So before lutetium, we have this S block. So S block group 2 is there. So if we can start from group 2, we have calcium. Before calcium, there are beryllium and magnesium in the S block element. Below calcium, we are having strontium, which is parallel with this yttrium group. And after that, we have this barium. Barium has this atomic number, that is Z is equal to 56. And lutetium has this atomic number 71. Now, you know in the periodic table, but here you can see this strontium has this atomic number 38, but this yttrium has this atomic number 39. That is the general case actually, because we know in the periodic table all the elements are actually in a specific period the elements are actually having this atomic number difference by 1. So by adding 1 we can go to the next element, because in the calcium we are having Z equal to 20, scandium is having Z equal to 21, titanium 22, vanadium 23, and so on. Here also strontium has the Z 38, yttrium has 39, zirconium has 40, and so on. But after that, suddenly in this 5D group, we are having this anomaly, because the barium has the atomic number as 56. That is quite okay, because it is 18 plus than the strontium. But then instead of having 57 atomic number, by having a great jump, and this between this 57 to 70 atomic number elements are missing. We are not able to find it. And then we are suddenly jumping to the 71, that is the lutetium. So why it is so? That should be an explanation, or we should, or how we will explain this thing, like they have done a mistake in constructing the periodic table. No, that is not the case actually. That is the case of the lanthanides. That is the case of the lanthanides. They are actually here. Between barium and lutetium, there are actually lanthanides. So lanthanide is also, lutetium is also a lanthanide. So from 57 to 71, 57 starts from the element as lanthanum. Then we have this cerium, we have PR, we have ND, we have promethium, we have samarium, and we will go so on. Then we will reach to a 70, that is ytterbium, and 71 as lutetium. So from 57 to 71 atomic number, in the middle is actually coming these lanthanides. Now what happens in this case of the lanthanides? So in case of lanthanides, the 4f electrons actually come into picture. Now we will read this thing first. The intervention of 4f orbitals happen as they must be filled before 5d. Because of their poor shielding, nuclear charge increases steadily, but size contracts as the nucleus attracts the valence electrons more tightly. So between zirconium and hafnium, these lanthanides lie, and as a result of hafnium, becomes, so as a result, size of hafnium becomes comparable with that of zirconium. So I will actually simplify this thing for you. So here we are having these d orbitals, that is fine. So after d orbitals and after actually covering this 5s orbital, there occurs this 4f orbitals. Now we all know we all know the shielding effect of s orbital is greater than p, greater than b, and greater than which is f. So f orbitals have very poor shielding power. F orbital cannot shield the electrons from the nucleus. So as we see here from 57 to 70, as the 4f electrons come into picture, we see the nuclear charge is increasing. From 57 to 71, it is increasing by 1, 57, 58, likewise it is increasing. But since the electrons is actually getting filled in the 4f orbital, which is a poor shielding orbital, so the nucleus, they are having some poor shielding. They cannot shield the nucleus from the outermost electrons. So the nucleus will exert its power on the valence electrons more. Thus the size will be contracted. So from zirconium to hafnium, the sizes should have been greater. But since this in between barium and hafnium, this lanthanide contraction takes place. This is popularly termed as the lanthanide contraction. Since this lanthanide contraction takes place, the sizes actually becomes lesser and lesser and lesser. That's why in case of hafnium, the increment will not be that much. That's why sizes of this zirconium and this hafnium, where hafnium has the principal quantum number 1 high than that of zirconium, it should have been much larger than that of zirconium. It does not become. Hafnium has the comparable radii with zirconium. You see, the hafnium has the radii as 159 picometer, but zirconium has the radii as 160 picometer. So this is the reason because of the lanthanide contraction, the sizes of zirconium and hafnium become very much similar with one another. So the next question is, why is there a significant increase in the density of the elements from titanium to copper? Now here you can see, here we are having this titanium in the extreme left side. Titanium has D2 configuration, and the extreme right before zinc we have this copper. Now you know from left to right, you know in our cases, since d orbitals come into picture, and we all know this d orbital is actually not a very good shielder. The s orbital is most, p is later, d is then, and last we have this f orbital. Now since these d orbitals cannot shield the electrons from the nucleus, this is the nucleus which is positively charged, and here are the valence electrons. Now, if in the middle there are d orbitals, d, and d is a poor shielder, the nucleus will attract the electrons more. That's why the size of the atoms become small. So from left to right, there will be a significant decrease that is actually written here in the metallic radius in the period. But if we are going from left to right, the size is actually decreasing. That is R, we are having R. The radius of the atoms are decreasing. But if as you are going from left to right, the Z, or the atomic mass, that is M, is actually increasing. Because titanium has Z equal to 22, but copper has Z is equal to 29. So from left to right, what happens? The R is actually decreasing, the M is actually increasing. So R is the radius. So if the radius, and we know the volume is actually directly proportional to the radius, because if we can think of the atom as a spherical unit, if it is considered as a sphere, then the volume of a sphere is 4/3 pi r cube. So volume is directly proportional to r cube. So volume will be directly proportional to r also. So as r decreases, volume also decreases. Now we know density is nothing but mass by volume. Now we know from left to right, the mass is actually increasing and the volume is also decreasing. So if the numerator increases and the volume decreases, so as a total, D also increases, because we are actually dividing a larger number by a lesser number. So density also from left to right increases. That's why there is a significant increase in the density of the elements as we go from left to right in the period. So from titanium to copper, since the mass is actually increasing and the volume is actually decreasing, so the numerator of this fraction is increasing, the denominator of the fraction is decreasing. So as a total, the density of the metal is increases. Because I can actually tell you with the specific example, suppose we are having this mass as 1 and volume as 2, which is equal to 0.5. Now, if we increase mass by 2 unit, it is having 3, and volume by 1.5 unit, we are having this 0.5, which is equal to 6. So if we increase the mass and decrease the volume, it is 6. So 0.5 to 6, there is a increase by 12 times. So it is 12 times high. So such increment is actually responsible for the increased density from titanium to copper. Now we will move on to the next question. It is, why is the enthalpy of atomization of zinc the lowest, that is 126 kilojoule per mole in the series from scandium to zinc? So this question has already been answered in a passive manner already in the preliminary slides. So I have told you guys when I was discussing about the increment or about the enthalpy of atomization. Now, since the enthalpy of atomization, I have told you it is directly proportional to the interatomic interaction, and the interatomic interaction is directly proportional to the number of unpaired electrons. So when it was case of chromium, chromium had the electronic configuration as 3d5 4s1. So it had 5 unpaired electrons. That's why its atomization enthalpy was very high. But in case of zinc, the electronic configuration is 4s2 3d10. So if the configuration is 3d10, all the electrons are actually paired up. So if all the electrons are paired up and then there is no unpaired electron, then there is very much less amount of interatomic interaction, because the number of unpaired electrons, if are more, the more will be the interatomic interaction. The more will be the interatomic interaction, the more will be the enthalpy of atomization. Then the more will be the melting point. Now we will leave aside the melting point. We are focusing on the enthalpy of atomization. In case of zinc, since there is no unpaired electron, all the electrons are actually paired up. That's why there is a minimum interatomic interaction for zinc atoms. That's why it is having very low enthalpy of atomization, that is 126 kilojoule per mole. Next question is, which among the following species is the strongest oxidant? Is it chromium 6, or is it molybdenum 6, or it is tungsten 6? Now, in case of the p block elements, the lower oxidation states are actually favored by the heavier members. You know, when we were discussing about these p block elements, when suppose we are having this boron group. So in boron group, we have boron, then we have aluminium, then we have gallium, then we had indium, and then we had thallium. Now, when we were discussing these p block elements, we saw in case of thallium, the attainment of +1 oxidation state was very feasible. Whether in case of boron, attainment of +3 oxidation state was actually favorable. So when we are discussing about the p block elements, the lighter congeners were actually stabilized by the high oxidation state. But in case of the heavier congener, the lower oxidation state was favorable. But the same is not actually applicable for the case of the d block elements. In case of d block element, the heavier elements favor the high oxidation states. So now we are having this chromium in the 3D, we have molybdenum in the 4D, and tungsten in the 5D. So from top to bottom, from chromium to tungsten, the principal quantum number or the heaviness of the mass actually increases. So when the mass increases, the oxidation state high will be more stabilized. That's why when we are talking about this molybdenum oxide or are talking about tungsten oxide, MO3 or WO3, both in the +6 oxidation state, they are actually very stable. That's why they are not reactive. But when we are talking about the chromium, it is the lighter most congener in the group, and it is having the compound as K2Cr2O7, potassium dichromate, or the Cr2O7 2-, which is also having chromium +6 configuration. So this chromium +6 compound is very much less stable. So the less is stability, the high will be the reactivity. That's why it is one of the highest oxidizing agent or one of the powerful oxidizing agents in acidic medium in the specific group. So K2Cr2O7 is actually, that's why used as a very powerful oxidizing agent. Now here the last two questions are actually very much important for the exam purpose. That's why they are the informative one. First one is the name a transition element which shows no variability in the oxidation state, which is scandium. So scandium is such an element, it shows only one oxidation state, which is +3. In all the transition element, we can see a variety of oxidation states. Chromium shows oxidation state 2 and 3, cobalt shows 2 and 3, nickel shows 1, 2, manganese shows 2, 3, 4, 7. But scandium is the only element, a transition element, or you can say the D block element, which shows no variability in the oxidation state. There is no variation. The reason is actually simple from the electronic configuration. So we have this electronic configuration as 4s2, 3d1. Now, if we can actually take up all the, and before that, we have the noble gas. This noble gas configuration is actually there. Now, if we can actually take up all the 3 electrons from the s and the d orbitals, so if we are having 3 electrons minus, then we are actually obtaining the configuration of a noble gas, which is actually very, very stable. You all know the noble gas electronic configuration is very stable. That's why scandium actually allows all the s and d electrons are actually should go from the 4s and 3d orbitals and leave it as sc3, scandium 3. So all the compounds that are actually there for scandium, they are actually scandium 3, scandium chloride, scandium triplet, etc. That's why scandium does not want to show any variability in the oxidation state, because in all the cases, it wants to attain the electronic configuration of the noble gas. The next question is, which among the 3D series of the transition elements exhibits highest number of oxidation states? Now, this answer is actually evident, that is, it is manganese. Now, manganese have this electronic configuration as 4s2, 3d5. So manganese has this electronic configuration 4s2, 3d5. So we are having 2 electrons, and here we are having 5 unpaired electrons. Now, if we are having this, so we are having these 7 electrons. Now it will start from state that is the +2, because if the 2 electrons are actually gone away from manganese, it will have a half-filled electronic stability configuration, which is D5, which is highly stable. That's why it is having the configuration +2. Now the more will be the number of unpaired electrons, the more it can show variability in the oxidation state. That's why in this case, manganese can go from +2 to +7 also. If we can actually take up all the 7 electrons from manganese, it will have the configuration of the noble gas. That's why +7 oxidation state is of manganese is equivalent to the +T state of the scandium. So that's why manganese shows the highest number of oxidation state. So in the next classes, we will discuss about the different properties of the transition metals, their oxidation states, their corresponding enthalpies, their hydration energies, and the rest of the properties.